Hello, it's me, Ryan. This is your first little lecture. We're going to finish covering chapter 20, either in this or in one or two extra videos. This is where we left off in class. So everyone should have these notes already. We started talking about sources of magnetic fields. They're always caused by, of course, moving charged particles. That means that any moving charged particle or anything with current will create a magnetic field. Those magnetic fields that are created by moving charged particles can affect other moving charged particles that are near or within them. So this is where we left off. Again, we'll never really use Biot-Savart law, but there it is. It helped us show the magnetic field produced by a moving positive charge. Magnetic field lines always form closed loops, of course. And then we talked briefly about the second right-hand rule. I wanted to add a little bit of that about the second right-hand rule, but we'll do that in just a moment. From there, we went on to talk about, or begin to talk about, something called Ampere's law. But because of all the changes in the semester, we're going to skip this. That means from chapter 20, we will have skipped, so chapter 20.8 and 20.10, we will not be covering. And that should say covering, so. Anyway, don't worry about those sections. We're going to move on into finishing discussing our sources of B fields, and then we'll talk about a couple very special B fields that we'll use in the class. But first, our little bit of right-hand rule number 2 review. So let's recall, of course, that right-hand rule number 1 always gives the direction of any magnetic force on a moving charged particle or on a current-carrying wire. And if you recall, we used a cross product for this one, and it was always the magnetic force equals QV cross B or IL cross B. And remember, we point our fingers in the direction of the first vector and curl them in the direction of the second. Our second right-hand rule always gives the direction of the magnetic field produced by a moving charged particle. Or the shape, if you want. It gives the shape of the field as well. But this gives the direction of a field, this gives the direction of a force, and so that's the easiest way to keep them separate in your minds. And it seems a little redundant, but as you see, I'm always saying moving charged particles because it always takes a moving charged particle to create or be affected by magnetic fields. And if you recall, in class, we decided if we had a current-carrying wire like so, where I is moving to the right in the picture, we could point our thumb in the direction of that current, and our fingers would curl around the wire to show the direction of the B field. And so if we imagine this pen is the current-carrying wire, if I put my thumb in the direction of the current, my fingers wrap around the pen to show what the B field created by the current would look like. And so if we look at this in a two-dimensional view, our fingers would come out of the board above the wire, and so we would see dots coming out of the page. And those would form loops, but if we continued to curl our right hand around, our fingers would have to go back into the page on the bottom of the wire, and so we would get X's down here. And of course, each of these would show some magnetic field loop. And we know the field produced by this wire then would look like that. This is a two-dimensional representation of something that is, of course, three-dimensional. And so, again, the right-hand rule number 1 always tells us the direction of a magnetic force, and right-hand rule number 2 always tells us the direction of the magnetic field. Okay, to conclude this video, I want to just give some fundamental equations that we know for specific types of current-carrying wires. And so we can show that for really the long straight wire. So this would be B fields produced by currents and so this first one will be a long straight wire. You can show that like so. And we just had a picture of this, but I'll show. There's my wire. We know that that current will be moving to the right. It could be going to the left, of course, and with the second right-hand rule, we can show that the B field produced by that wire will be, again, dots on the top, X's below, and they'll form closed loops. Now this long straight wire has a known magnetic field equation, which I can give you now. For any long straight wire, we'll say mathematically. So this was the diagram. Mathematically, we know that the B field produced by that wire will be equal to mu sub O I over 2 pi r, where r, so we'll give you some definitions. And this would be the magnitude of the B field. I is the current. R is the distance from the wire. And mu sub O is called the permeability of free space. It's a constant associated with magnetic phenomenon, and it's always equal to 4 pi times 10 to the negative 7. And this is given in several different types of units. The one I usually use is Newton per amp squared. And so this is the equation for any B field produced by a long straight wire. And so if you're given a problem where you have to use the B field produced by a long straight wire, you ought to use this equation. We would derive it with that thing we're skipping called Ampere's law, but who cares? The next sort of fundamental shape that we would use a current carrying wire to produce would be taking this straight wire and turning it into a loop. If we did that, we would get a picture for a current carrying loop, and I'll show that now. So this would be a current carrying loop. We'll show you the diagram first. We can have our loop like so. It doesn't have to be a circle, but why not? And we could put some current going through this loop in a counterclockwise direction, because that's the way everything seems to go in the universe. And now if we were to apply the second right-hand rule to this current carrying loop, if we put our thumb in the direction of the current, we can have our fingers curl around the wire to show the direction of the B field. And so at that point, the current's going up, my thumb is in the direction of the current, and my fingers wrap around the wire. So inside of that loop, my fingers would come out of the page. If I try the current in any point, my fingers will always come out of the page when I'm inside the loop. And so inside the loop, we could show that there's a magnetic field going out of the page, which would be dots. That means, of course, that there would be X's outside of the loop. But if you really try to imagine this circular B field, it might look something like a donut. Anyway, the mathematical equation for any circular loop of current is the following. The magnitude of the B field for the loop is given by, and it's basically the same as the current carrying wire, except it's missing a factor of pi. So we get mu sub O I over 2r, where r is the radius of the loop. And so this B loop would be the magnitude of the B field inside the loop. You might note, for multiple loops, this equation just gets a factor of n, where n is the number of loops. So it'd be mu sub O n I over 2r, where n is the number of loops. Okay. Lastly, if you take multiple loops and line them all up, you get something that we very fondly refer to as the solenoid. The solenoid is really a whole bunch of these loops all connected electrically so that they form this very long so that solenoid will have some length L. It will have some number of turns, N. And it will have some radius, R, like so. So if you imagine the solenoid is taking a whole bunch of these loops of current and putting them all together so that they make a tunnel of current, basically. But all of these different loops are electrically disconnected, meaning these coils must be covered with some dielectric material, usually rubber or some sort of paint. Anyway, for n loops, this solenoid will be L long with radius R. The mathematical equation for any solenoid is the following. So the B field, so we'll say mathematically, the B field, the solenoid, is equal to mu sub O little n I, but little n is really just big N over L. So this will be the equation for any B field inside a solenoid. This is the magnitude of B inside the solenoid. So that has to be some point inside of there.